some measurement where you measure position and momentum more accurately than you could, and you show that, well, if you impose the position, momentum, uncertainty relations on the apparatus, then you won't be able to beat it, on whatever you're trying to measure. So that's kind of a relative consistency condition. The other kind of argument, like in this case, you derive one uncertainty principle from another. So in this case, we're deriving delta E, delta T from delta P, delta Q. But if you don't put in some quantum input, obviously, you wouldn't be able to get any quantum input out, any quantum output, I think, if you didn't input something quantum again. The other form of the argument, which I will give if there's time, but I suspect there won't because we have a lot to cover, but if there's time, maybe I'll give the other version of the argument that I came up with, which doesn't actually use any uncertainty principle as such, but it uses something closely related. It uses the knowledge of what the minimal dispersion in position is in the ground state of a harmonic oscillator. So if you like, that's coming from the Schrödinger equation, but of course, if you trace through why the ground state of the harmonic oscillator is not just something sitting at rest at the origin, it's really, in a sense, because of the uncertainty principle. So it's kind of implicit there, I would say, although it's not explicit in that form of the argument. But you have to have some, certainly without some quantum input, you won't get any uncertainty relation as output. Yeah.
It also seems as though the interpretation of what delta P and delta Q mean, there's a sleight of hand there, going from what its mathematical meaning is to interpreting it.
There can be, although I didn't think there was. I don't think it needs to be like that. I'm not sure why you say that. Maybe there is a little, there's always a little jump, especially in the case of time energy, there's always a lot of doubt exactly if there's a unique interpretation or there are several, or which one applies in a given case. And there's certainly a certain kind of gap between arguments that say the position and momentum are intrinsically indefinite by a certain amount, and a kind of conclusion that you might draw that if you measure the position, you disturb the momentum. So it has different facets, and maybe the way of getting from one to the other is not always as clear as it could be. That I'm not sure. I think that there's an actual cheat going on. Did you have some particular instance in mind?
Bridging a gap between the quantum world to the classical world without saying much about what's going on. Like delta P and delta Q was a statement about expectation value.
Well, that's very fair statement. So, but that's part of a much broader problem. Right. Is that the way of connecting the quantum formalism to the real world is I think still obscure in all over quantum mechanics, not just in connection with the uncertainty relations, but I think that's a general thing. And it has to do with the fact that we don't know the interpretation of the quantum formalism. For example, the wave function, we don't know how to think about it, except in the context of some operational kind of story. So this becomes a whole other discussion, which is, I think, an interesting discussion, but we probably shouldn't have it here. But my own feeling is that there's a big unanswered question that hangs over all of this, which is, what is the physical reality to which the quantum formalism refers? And that's never been answered satisfactorily. That's why we have a field called quantum foundations, which is trying to answer that question. Or some people might express what they're trying to do in a slightly different way, but I think that's one way of thinking about what they're trying to do. And that's why going from any statement given to you, formal statement in the quantum theory, to any statement about reality has a kind of sleight of hand, if you like. or a kind of fuzzy area or something. So I think I agree with that, but I think uncertainty principle is only just one example of a much more general effect of that, or a problem of that sort. So, yeah.
I think in principle you could be more precise in how you interpret delta P and delta Q for the purpose of that argument without having to present a full-blown interpretation.
Perhaps. We didn't. That was your point, yeah. So, well, can you say very quickly in what way, where you think it could be more precise and should be, or was not?
Well, you sort of interpret delta P and delta Q as meaning like our lack of knowledge of these quantities.
Well, but that's exactly the thing we're talking about.
Yeah, it's not clear how that relates to this expectation value of an operator.
Well, we didn't introduce expectation values of operators.
Well, that's what delta P and delta Q are.
No, not in that argument. So in that genre of arguments, they're sort of mixed classical and quantum. I mean, if you say it's the expectation value of an operator, I will say, what has that got to do with anything, right? Then that does, in my view, that does bring in the whole broader issues that I was raising. But what we're saying there is that in that discussion, delta P, let me think. In the context of that kind of discussion, the question is, could we simultaneously determine the energy of this event that took place, which was this decay particle, and the moment at which the decay happened? And so what delta P and delta Q represent, it's could we determine it as external agents with instruments and so on. So what delta P and delta Q need to represent there is our uncertainty about position and momentum. It's not the claim that there really isn't a precise position and momentum of which we're uncertain. It's just a claim that we cannot experimentally pin down those numbers more accurately than a certain amount. So I don't see, and then, of course, when I discussed this particle on the spring, this box, what we were weighing in order to determine the energy. If I don't know the position, I mean, there is something of the nature you're saying, which is that I'm assuming that if the position is uncertain if the position is uncertain, then our knowledge of the mass is uncertain. But I'm assuming that the momentum uncertainty that goes with that position uncertainty will actually manifest itself in some sort of bouncing motion of this particle. So I'm really attributing that momentum uncertainty to a genuine physical value for the momentum. If we can't know what the momentum is, then it should mean that we can't know the velocity. And so the velocity could be anything in that range, and and if we make the position too precise, then there is a genuine implication that if we look a little bit later, this will have had a large, because I made the position precise, I made the momentum very imprecise. That should be interpreted as a kind of statistical distribution of momenta, so that in a later time this is going to be bouncing way up here or way down here, and the attempt to measure will fail for that reason. Right? So there is a kind of, I agree with you in a sense, there is a kind of going back and forth between uncertainty in knowledge and meaning that the thing of which you're uncertain will have the physical consequences that you expect it to have, right? So you're treating it as if it's a classical object which actually has some statistical uncertainty. That's the only way in which you're putting in the uncertainty principle in. And that's the character of all these discussions. If you look like this Heisenberg microscope discussion or any of those that derive an uncertainty relation of one sort from an uncertainty in another sort, they always do that. It's a kind of, you switch back and forth between a classical way of talking about it, and then at some point you stick in this spread or this uncertainty. And so in principle there should be, I mean, these thought experiments were important historically, and I think they add a lot to the intuition. But now that we have quantum mechanics as a full-blown formalism, you might say we should be able to carry out the whole discussion without that kind of semi-classical reasoning. And I think that's correct in principle. And maybe you could in some form or other, but I think once you try to do that, it does raise this general question, question of the more general nature. So all I would say is the kind of argument that I described there is within the whole genre of uncertainty principle discussions, and it fits in there. But that whole genre can be questioned whether it's the last word. It shouldn't be the last word. Okay. So, yeah, I don't know if there's anyone who didn't get this handout on tensors. I have a spare copy, and if you didn't get it, anyway, as I said, it's posted on the website for the course. Was there something else? So where were we? Yeah. So as I said, if there's a little time at the end, which I doubt, I can give the other form of the uncertainty principle argument. But let's go on where we had left off, which was defining tensors in a general way. So tensors, as you know, are a very basic concept for relativity, and they're also, interestingly enough, a very basic concept for quantum mechanics, the way of combining composite systems which consists of two kinematically independent subsystems, possibly not even interacting, is you make the bigger Hilbert space by a tensor product of the smaller Hilbert space. And a lot of the subtleties, the mathematical subtleties that make tensors hard to understand in a certain sense, actually manifest themselves there as physical subtleties like entanglement and things related to entanglement. So there is, if you find tensors difficult, I think there is actually something that is rather difficult about them. On the other hand, I wouldn't want to exaggerate that. There's some sense in which they're completely straightforward mathematical notions. So the goal now is to just give a precise mathematical description of what is a tensor and what is tensor product and what is a tensor space. But in order to do that, we had to first define, remember we started with some vector space, which typically for us will be the tangent space to space-time manifold at some point P. And as you no doubt know, there are both contravariant and covariant tensors or vectors, and what are called contravariant and covariant tensor indices. And they correspond not only to this tangent space, but to its dual space, which is, we defined last time, which I called V star, which you can think of in many different ways. And then all the tensors that we will deal with will be built out of these two vector spaces, V and V star, these two. In general, you can do this. You can form tensors out of any kinds of vector spaces, but these will be the ones that are important to us. So I have to actually say a little bit more about the relationship between this V and V star, which will be crucial for the notion of contraction that you use in tensor algebra. So what we're doing now is just tensor algebra. Then, in other words, we're not taking derivatives of the tensors fields yet, or the differences of tensors at infinitesimally neighboring points. That'll come next. But first we want to just discuss the algebra of tensors. So imagine you're just at some fixed point in the manifold and you have some fixed vector space. So we define this as the set of linear operators from V to the reals. And the consequence of that is that just by definition, you can put together. I also gave, by the way, I also gave a geometrical way of thinking about vectors, and covectors. So vectors were arrows, as people normally think of them. Covectors are can be thought of in terms of a set of parallel planes with a certain orientation given to them. Actually, I think I asked, I don't know if anyone did it, but I asked if you could think what would be the geometrical rule for the sum of two covectors given that. Anyway, however, we'll just think now primarily algebraically. So what this definition of V star amounts to is that there's a rule for combining a vector and a covector and getting a scalar. And it acts linearly on both arguments. So this is called the scalar product or inner product to distinguish it from outer product, which we'll define in a second, which is another name for tensor product. That what it does is it tells you if you take an element of V star, a covector, and an element of the vector space, so I call them omega and V, and you put them together, put them together, you get a scalar, which can be notated in many ways. So you can just write it like this, or you can write it omega of V, sometimes when you're thinking of this as being the linear map from V to the scalar. So this is applying that linear map to that vector, V, or you can write it as omega dot V, or you can write it also, since you know which is the vector and which is the covector, it really doesn't matter which order you write them in. And in fact, if you think of it, if you write it this way, you can think, the way we defined the covector originally is we imagined fixing a covector and varying a vector, and that gives you a linear map from the vector space into the reals. On the other hand, we could take the opposite point of view. We could say, fix a vector V and consider the set of all possible covectors. Then that also defines a linear map. If you think what it means to add covectors, you can easily see that that also defines a linear map from the space of covectors into the reals. So we could just as well think of a vector as being a linear map from the covectors right to the reals, which in the space of those linear maps, using the same notation, we would call V double star, the double dual of V. That's the dual space of the dual space of V. And so in an obvious way, every vector can be regarded as an element of the dual space. And in fact, I claim, so what this does is it shows you how to find, given a vector, it shows you how to find an element of V double star that corresponds to that vector. But in fact, the claim is that every element of V double star comes from such a vector. So you could just as well, and furthermore, no two elements of V double star, no two different vectors give different elements of V double star. So we can actually think of the vector space, we can actually think of V double star as being V. So I put a little quote here, quotes meaning that it hasn't been defined to be the same, but it's in some natural sense identifiable as essentially the same space. So how can we see that? So I'll give a little proof in a second, but the consequence that that has is that there's a perfect duality between the notion of vector and covector. We could have started with covectors, and then we could have defined vectors as their duals. It's just, in some sense, more natural to do it the other way, but you could start with covectors as these geometrical kind of things and so on, and produce vectors from them. So it's important to be aware of that sort of symmetry between the way vectors and covectors enter into the story. So how did we prove? How do we prove that vectors and that v double star equals v? Well, I've just given you a map. I'll just give it a name that takes vectors. Okay, so I've just given a name to that map, and so if I take a vector v and regard it as a linear functional on covectors, then I'll call that resulting thing as I of v. Sometimes people, you might see this in some literature. Sometimes people also give it the name of v double star, but I'm just calling it I of. That could be a little confusing because it suggests it's the dual of v, but there's no actual v star in that notation. There's just v double star. So this is another notation that you might see, but I'll just call it I of v. So it's the vector, it's the linear map defined by the property that I of v, when I apply it to a covector omega, it's just the same as the inner product of omega and v, if you like, omega applied to v. Now, first I claim that this map I is injective. It's almost obvious, but what does it mean, injective? Injective means that, I have to prove that it's bijective. I have to prove it's both injective and surjective. That means that there's a one-to-one correspondence then between the elements of v and the elements of v double star. That's why I can equate them to each other. So let's look at inject. So the first thing says injective. Remember, that means that two different vectors, little v, if they're not equal, then I of v is not equal. So you don't lose information by going from v to I of v. And in the case of, since we're dealing with linear objects, that's true if and only if, this is a sort of general thing that comes up a lot. So if you had sort of v, if you wanted, the question here, just do this as an aside, the question is that if I of v1 equals I of v2, does that imply v1 equals v2? But since everything is linear, I haven't proved it, but you can easily check that this map is linear. I said it anyway. That's the same as questioning whether I of v1 minus v2 equals 0 implies v1 minus v2 equals 0. So it's really just the question, is I of 0 equal to 0? That's what you have to check if something, to show that a linear map is injective. So if we apply it to what do I have it? But this is not. It's the question of whether if I of v equals 0, that implies that v equals 0. That's the question. So so suppose I of v is 0. What does that mean? That means that you have that I of v is a covector which annihilates every I of v. Sorry, is a whatever covector that annihilates every vector. Looking at this equation, it just means that v is a vector that's annihilated by every covector. But there is no vector that's annihilated by every covector other than the 0 vector. I mean, if you look at that picture, you can see it, or in many other ways. It's obvious. I mean, it's easily proven. So it is injective because this statement is true. The other one that's less obvious is the surjective. How do we know that we get every vector, every co-vector from a vector in this way? But that we can do. That's much less obvious in general, but in this case, it follows from a dimensional argument that the dimension of V is the dimension of V star. We haven't proved that yet, but it's sort of probably known to you. And if it's not, we'll prove it when we come. We'll have the ingredients for the proof when we come to talk about basis. So given a basis of the vector space V, which just consists of four distinct linearly independent vectors, since we're in 4 dimensions, given a basis of that, we can easily produce a dual basis, a basis for V star, called the dual basis, and it means that V and V star have the same dimension. So we've just proved that this map I is an injection, and if it's an injection from one vector space to another of the same dimension, then it has to cover that whole vector space. If it weren't surjective, if there was something missing, left out when you map V into V double star, then V would be found inside V double star as a subspace. That would have to be a subspace of lower dimension, but it can't be of lower dimension because this is an injective map. So for finite dimensions, it's always true that V is equal to V double. We can identify V double star with V. Maybe just as a comment, I'll say that in infinite dimension, there's no reason why that has to be true. So in a more general situation, you start with V, you get V star. From that, you could get V double star. I don't know how far this can go. Perhaps it can go forever. They could all be different. What we saw here is that V double star is at least as big as V, but it could be bigger. If it were, then we'd have a lot of tensors would be much more complicated objects than they already are. But in finite dimensions, we don't have to worry about that.
Sorry, how do you know that V double star could be bigger than V?
I don't know that it could. I haven't proved that it could. I'm just saying from what we've seen that it cannot be smaller, because we can find a copy of V inside V double star. But it could be that it's bigger. And in certain infinite dimensional examples, it actually is bigger. But I don't know what the most generic case or the most general kind of thing that can happen in infinite dimensions. It doesn't happen in the cases that you're very used to in physics. So when V is a Hilbert space and you use the adjoint or the conjugate, I don't know what the word is that takes you from this to this. When you flip, what do you call that? Anyway, that dagger, yeah. Okay. When you do that operation, you define this in such a way to be a continuous linear map, and then using the Hilbert space topology, then it turns out that V star and V are actually themselves isomorphic, just as in the sense of having the same dimension, and that's just as they are in the finite dimensional case. And then it turns out that there's actually more than just having the same dimension. There's actually an anti-unitary map between them, which is this dagger map, right? And then, so basically, V and V star could almost be identified, but not really, because not until you have the metric, which allows you to identify V and V star. But in any case, then V double star will be the same as V. So it doesn't happen in a lot of the examples that you're used to, but it happens in other cases. But anyway, in finite dimensional, this series always terminates here, and we only have, starting with V, which is for us the tangent space, we only have 2 basic kinds of vectors to work with. And now we have to form from them tensors. so how do we form tensors? Yeah.
In the infinite dimensional case, V star isn't it? Do you take it to be the space of all linear maps, or do you have restrictions and some bounded or something?
Yeah, absolutely. Yeah, all continuous or bounded, if you like, linear maps. The same. I mean, two words for the same thing. Yeah, you take it to be. Otherwise, it would be a huge. I don't know how. Probably an uncountable. If you just took the algebraic properties, right? So as I already said, I think when we discussed the different meanings for a tensor, the way that we'll think of them first off, or most in the original form, is as products of vectors. But what does it mean? Or now we have to say products of vectors or covectors. But what does it mean to form the product of vectors? So if you think about it, you don't know the answer probably, or there's nothing that sort of presents itself as naturally being, cross product. Well, that gives you another vector. So this is just we just give ourselves the ability to form products, and we just say that they should behave as products behave, and beyond that, we impose nothing on them, and we call it tensor product. So let's take two vector spaces now, which for the moment I'll just call V and W, because they might be both V, or one might be V and one might be V star. So I'll just call them VW. And I'll take a vector, V and W. I'll take a vector in V and a vector W in W, and I'll just say that there's now a tensor, which is the product of V and W. Okay. But that's not enough. Not every tensor is a product of a vector from V and a vector from W. In general, a tensor is a sum of such products, and we have to be able to add them. We want this set of tensors to be itself a vector space, to have a notion of addition, like if you want to add two stress energy tensors, for example, or take the difference of two metrics, or so on. So we're also going to require that it have a linear structure. So actually, I need to take a whole set of vectors in V and a whole set of vectors in this other space, W, and then for each one of them, I form their product, and then I form the sum over N. Okay. So this is a tensor. This is an example of a tensor. Obviously, I could have taken more spaces, and that generalizes in an obvious way. But this is an example of a tensor made from a product of just two vectors, or a sum of products of two vectors. So this is the general tensor, and the set of all such tensors makes up itself a vector space, which we call the tensor product of the vector spaces V and W. So notice the same symbol is used here, but it has a different meaning. Here it's the particular tensor that's the product of V and W, or Vn and Wn. And here it's the space that's made by taking the set of all sums of products of this nature. Now we want, as I said, we just made up this product. We just invented it for ourselves. But we wanted to have the properties that a product has. This is also, as I think I said, called, but maybe should write, that's called outer product or tensor product. This is actually, I've never heard the word outer product applied to two spaces, but it may be that it is. But this is certainly called the tensor product of those two vector spaces. Now we want it to have all the properties of a product. What are those properties? So it should be like associative, distributive, all the things you might have learned when you were studying arithmetic. it should have the same properties. So this means that certain sums that we write down like this represent, although they may look different, they represent the same tensor. And so we need to understand when that's the case. So not every sum represents a different tensor. It's actually, if you like, a tensor is somehow an equivalence relation of such sums of products. And what are these relations that we need? Well, first there's this associativity. So if I take A tensor B tensor C, that should be the same as A tensor B tensor C, and so on. And then distributivity, if you A tensor B plus C is equal to A tensor B plus A tensor C, and so on. I could also write it the other way. And then there's the even more trivial laws, like if I multiply a tensor by a scalar, what do I get? And how is that related to multiplying it by a vector? So, how is that related to multiplying this scalar by one of the factors of the tensor product? So that's in the rule that lambda A tensor B is equal to lambda times A tensor B. And it's also equal to A tensor lambda B, right? So these are all things you would do without thinking twice. But they're part, if you like, they're part of the definitions that tell you when two sums represent the same tensor. So given all these rules, then if we can convert, given two such sums, t and t prime, suppose t prime was equal to the sum of v prime m tensor w prime and some other tensor here. If we can convert, this is supposed to say convert, t into t prime by these rules, then we declare them equal. Okay? So just to take a very trivial example, if I would take, this is a very, very trivial example, but if I were to take, say, A tensor B plus minus 1 times A, well, let's just say, I can just write it as minus A, plus minus A tensor B. Okay, so that's a different sum because A is not the same vector as minus A. But by these rules, obviously, I convert it to A minus A tensor B, which is 0 tensor B, which is 0, which we could derive from these rules. So that's a trivial example, but there are more subtle examples that you would find it harder to immediately see. So the real question is, when can you convert t to t prime? And I won't go through. One can give a precise statement of when t and t prime represent the same tensor. As I mentioned before, that's really the statement is when does t minus t prime represent the tensor 0. So really you're just asking when does a given sum like that equal 0. And I won't give the rule. It's in the notes that I handed out. So in the notes you can find an algorithmic procedure, an obvious sort of algorithmic procedure to test whether two tensors are equal. And you can also find a formula that'll tell you if you can find a set of equations, that if you can find a solution of those equations, then it means that the two tensors are equal. And if you can't, then they're not equal. So if you want a precise statement, just look in the notes. Yeah.
Can you write it this way? If say you have GAB, the metric, can you then write it as some vector A times vector B?
Yes, absolutely. We'll come back to that.
Okay.
Yeah. You certainly can do that. Right? In particular, that's what you get when you find an orthonormal basis. Then you can express the metric in terms of products, squares of the basis elements, sum of squares.
Does that mean that if something like the Christoffel sum was not actually a tensor, then you can't write it as some vectors multiplying each other?
Well, that's true, yes. It means geometrically you can't. Of course, it doesn't mean that you couldn't express, we haven't talked about components yet, but it doesn't mean that you couldn't express the components as products of components of vectors, but that would vary from one coordinate system to another. The ones you would choose would vary from one coordinate system to another. Yeah.
So I'm still just not sure what the notation is when you write the ends underneath.
Oh, that's just the label, just an index for the. You might ask why I wrote it underneath.
Not just why you wrote it, it's underneath, it's behind the other board. More so, I'm wondering why we're. I mean, it looks like you're adding up component, you're multiplying component by component.
No, there's no components.
Well, you have a sum.
I mean, I could have given them all different names, so I just mean something like this: A tensor B plus C tensor D plus E tensor F.
Right.
So I was just I just wanted to write a general expression that covered all those possibilities.
So we end with labeled different vectors?
Yes, right. So yeah, I should have said that. So V1 would be A, W1 would be B, and so on. V2 would be C, and whatever. So it was just a short way of expressing. This is the generic form of a tensor. Thanks.
So do you write it underneath so that we don't confuse it with the components of the vector?
That's right. Yeah, that's because I'm thinking ahead to. So these ends are supposed to be labels for different vectors, not components, not indices that correspond. They're not vector indices. In a moment, we'll define what are called abstract indices. So, but these are neither abstract nor concrete indices. They're just compact ways of talking about a whole sequence of vectors. Yeah. Was there another question? No? Okay. So that's it, right? So I mean, I told you the thing in the note, the thing in the that you'll find if you look in the handout is just an effective algorithmic procedure for answering this question: can you convert T into T prime by successive application of these rules? But this is the definition, right? So now we've defined tensor product of two vector spaces, and the extension to 3 is, I think, obvious. So, let's see. Oh no, I guess we want to leave it like this. So let me state something which we won't prove, but we'll see that if we choose we'll define, or we won't define, we'll study bases for these vector spaces. So given a basis for this vector space V and a basis for W, we'll see that suppose that this basis, now I'm using the same thing, so E1, E2, E3, I don't know why I did this, but make them boldface. Anyway, these are bases for V, and then given a basis for W, which I may call F1, F2, so F, let's say EM, and say EN. So given a basis for this and a basis for this, then, as we'll learn, the set of vectors of the form EJ tensor FK where k and j vary independently, form a basis for V tensor W. It doesn't add anything to make them boldface, and it might be confusing. So given a basis for V and a basis for W, you get a basis from the products. And that has the consequence that, that the dimension of V tensor W, which is, of course, the number of basis elements you need, the number of members of a basis, is equal to the dimension of V times the dimension of W. So that's a general fact about vectors, about tensor spaces, which is also probably in one form or another already familiar to you. So in our case, we'll almost always be dealing with four-dimensional vector spaces. They're duals, which are also four-dimensional. And so the dimension of a tensor space will just depend on the number of factors, and it'll just be 4 to the, 4, 16, 64, whatever, depending on which kind of tensor space it is. So our tensors will normally, as I said, come from V being the tangent space, and the kind of tensors we'll consider will be V, V star, V tensor V, V tensor V star, and so on, but not too much so on. You rarely will see tensors with more than 4 indices on them, so that is, you'll rarely see more than 4 factors here in the product. And we might as well, just for uniformity, we might as well regard scalars as special kinds of tensors of rank 0, as it's called. Sometimes you see the word rank. This would be called rank 2. Another word you can sometimes use for it is valence 2. When we come to use the index notation, it'll just be count the number of indices is just the rank. And so we can think of a vector as a special case, a tensor of rank 1, scalar of rank 0. Here's another one, another space. So here, I wrote this one because we know that the metric belongs in that tensor space. So we're almost done with, well, no, not quite. So there's 2 more. So there's another thing I wanted to mention for those who are mathematically inclined, although I won't use it. If I were to use it, it would simplify some of the proofs that I won't give. So it's probably, that's one good reason. But I encourage you, if they're not absolutely clear to you, to think a little bit about it, which is called the universal mapping property. It's possible to think of these tensor spaces as generated from the vector spaces of which they're products. Where did they go? Huh? Oh, here they all are. Yeah. So it's possible to think of these as defined as solutions of a certain condition called a universal mapping problem or property. They have the universal mapping property. And if you think of them, that you may run across this definition if you're more mathematically inclined. And if you do use it, then it makes it easier to see, as I said, that certain things are well defined. For example, the definition of contraction. It'll be easier to prove that it's well defined. The way we're doing it, every time I define something, I have to go and check that it's consistent with these equivalence relations that we've defined on tensors. That's one comment. Okay. Then the next thing is, in fact, contraction. So why is this? Oh, yeah. So most of tensor algebra is kind of completely straightforward and trivial. But there's one thing that perhaps is not, which is the notion of contraction. By straightforward and trivial, I mean it's just built into this idea that you can form sums of products of vectors. However, contraction is a little more subtle, and it comes from the fact, it's not a general fact, but it has to do with the fact that we're taking not arbitrary vector spaces, but just we're just using V in its dual space now. So W in this case really for us will be either V itself or it'll be V star. But between V and V star, there's an inner product, which I somewhere wrote down up there, I guess. So because of that, if a tensor if it's built out of V and V star, or it has within it factors of V and V star, you can bring them together and form a scalar and kill off two of the factors in the tensor, producing a tensor of lower rank. That process is called contraction. So the definition is completely straightforward. If we define tensors this way, that's nice. However, as I said, then there's a consistency check. You have to check basically that when you contract two tensors that are equal, you get two equal tensors. And as usual, that really means if you contract the zero, if you take a tensor that's secretly zero, like this one, wherever it was, and then form a contraction of it, then you'll get the zero tensor. So how does it work? So let's look at an example. Suppose that suppose that this tensor belonged to V, say 2 copies of V and 1 copy of V star, covectors. So it's a product of 2 vectors and a covector, or more precisely, it's a sum of products. A term in the tensor is a product of 2 vectors and a covector. Well, we can't contract vector with itself, but we can, because we don't have a metric yet, but we can contract a vector with a covector using the inner product. So let's look at a contraction. So this would be, in the tensor T, this would be a contraction between its second with its third factor. When we come to use the index notation, it'll be a contraction of 2 particular indices with each other. So let's take, so suppose it's of this form, A tensor B tensor omega plus, I think this will illustrate the general case, C tensor D tensor lambda. So I'm sort of making an informal convention that I'll use Greek letters for covectors and Roman letters for vectors. There's a mistake here. So now when I apply this contraction process to it, what happens? I get a new tensor. And what is it? Well, if you look at this, it's obvious what it should be. We've done away with 2 factors, so it'll actually be just a vector in this case. We've been asked to contract the second with third, so that means it's A times the inner product of B with omega, and then we do it on the other term here, and so it's C times the inner product of D with lambda. Now this, of course, is just a real number, and this is a real number. So this is just a real multiple of A plus a real multiple of C. So in this case, it actually belongs to V. Of course, if I had had more factors here, like if I had had V, another factor of V star, then it would belong to V star tensor V. Basically, it crosses off 2 of the factors of the spaces that went into making the tensor. So we could call this contraction of T on second and third. I don't know what is a good word. Indices would be an even better word, right? But we haven't yet defined the indices. It will be exactly indices as soon as we introduce indices. So for now, anyway, it's the second and third places or whatever. To make this, so for consistency, you need to check, and I encourage you to actually check it using one of the, using whatever method you want, but you could use one of the two criteria for equality of tensors that are in those notes, for example. You need to check that if T1 equals T2, then T1 prime equals T2 prime, which is, as I said, is really the statement that if T equals 0, then T prime, I mean, it suffices, the only thing that's not sort of trivial in the proof is that if T equals 0, then T prime also equals 0. So as I said, here's a place where if you had this universal mapping property, it would be this definition. I could have given it just for one simple tensor, which is a product of the vectors, and that would establish it in general. Just a mathematical comment. Okay, so we define contraction. When we finish all this, then we'll introduce components, and we'll see how all these things look in components, and then they'll probably look more familiar to you. But it's important to understand that they're defined independently of any choice of basis, any choice of coordinate system. The other thing that's not, I don't know if to call it non-trivial, but it can be confusing, which along with contraction. So the second thing, which along with contraction is maybe that's not completely trivial and which can in fact be confusing, is symmetry operations on tensors. For example, when we say that the metric tensor, I guess it was here, when we say that the metric tensor is symmetric, what are we saying? So let's consider a tensor. So to see what that is, let's consider a tensor that belongs to V tensor V, or it could be V star tensor V star. It's either a product of two vectors or two covectors, but what it shouldn't be is one vector and one covector, because symmetry has to do with permuting these factors, and it doesn't make sense to permute them if they belong to different spaces. So what the symmetry operation does, if I call the factors U and V, it takes that tensor and it turns it into the tensor V tensor U. Right? So the statement is or V star tensor V star, but not V star tensor V, for example. But for either of these two types of vectors, I can permute the two factors. If I took something that was in U in V tensor V star and permute the factors, so this is turned one tensor into a different, in general, tensor. If I were to work with something that was like omega tensor V, I could, of course, write V tensor omega. Oops. But what that would do would not be an operation on some fixed vector, a tensor space. What I would be showing by doing that was, in fact, an isomorphism, that V tensor V star is somehow isomorphic to V star tensor V. So I would have shown you how to go from the one space to the other. But this goes from one space back to itself, and so it's actually an operation, a symmetry operation within that vector space. Notice there's a subtlety here, which is that I'm regarding these as a priori different spaces, right? I'm paying attention to the order in which I write the tensor product. Okay, but anyway, this is the definition. You see what the definition, this is a definition for simple tensors. Obviously, if I were to write a more general tensor, like I did before, it would just, there'd be the symmetry operation. I could call this T, and I would call this other one, say, T tilde. It's just the one with the order of the factors reversed. So that's the symmetry operation. When we say that G tensor like the metric tensor is symmetric, I keep covering it up. When we say it's symmetric, we're saying that it's left invariant by that symmetry operation. Okay, so we'll come back to that in a second. And someone asked about, it'll ultimately have the meaning that I can write it as a sum, not of arbitrary products, but a sum of squares. By squares, I just mean like V tensor V. So both of these, are well complete. I've given you the definitions, but you can see that the definitions of both of them are a little awkward. They involve going back to the explicit representation of the tensor as sums. When you work with indices, it's much easier to notate these operations, and that's one strong motivation for using indices. Another motivation for using indices is that it shows you what kind of tensor it is. I mean, if I just write T here, unless I show you how it was produced, you don't know what kind of tensor it is. Does it belong? Is it a vector? Does it belong to V tensor V or what? By using indices, you also make it explicit. You make it manifest which space of tensors it came from. In other words, how many factors of each type do you need to build up that kind of tensor? So like in the case of the metric tensor, you see just by looking at the indices that it belongs to this vector space. If I just called it V, you wouldn't see that. So there's a great convenience in using indices. However, there's also a danger that it makes you think that you're just talking about arrays of numbers, just components. So a way of sort of having the best of both worlds is this notation called abstract indices. So I want to introduce that now. That's the one I think that's used in Bob Wald's book, although I don't think Bernard's book uses it. Is that right? Those who have been reading the books, if you remember. I don't think he actually uses the abstract index notation. But you'll come across this a lot. And the great beauty of this notation is that once you become comfortable with it, you don't have to, I mean, you can become comfortable, once you become comfortable with it, you can write the same formulas you would have written using the concrete indices, and you never see the difference, almost never see the difference. Then certain things could be a little confusing if you're not sure whether the index is meant to be abstract or concrete. But in general, the formulas look exactly the same. So this index notation, this abstract index notation, also provides you some sort of seamless interface. It provides for a kind of seamless transition between the notion of tensor as a geometrical object, an algebraic object like we've defined it, and the notion of its components, so tensor as just an array of numbers. So what are these indices? So these indices are just letters that you attach to the symbol that represents the tensor that shows you exactly how it was built up, as I said. And second of all, by matching indices, it shows you contraction. And it also shows you, by permuting indices, it shows you symmetry operations. In fact, you can also think of these as pictorially, which is becoming, well, some bunch of quantum information people are actually now popularizing these pictures. So let's take an example like the metric G. So using the index notation, we use this A and B. So I think for now what I'll do, by the way, is I think for a little bit I'll try and keep to this convention. Will be Roman letters, like maybe preferably from the beginning of the alphabet, A, B, C. And we won't have concrete indices yet, so I won't worry about how to represent them. So these are abstract indices. That means that's showing you that it belongs to V star tensor V star. You could also introduce a kind of, and here's a vector, let's say, a tangent vector, so I'll represent it like that. You can also even use sort of lines coming out to represent these indices A and B. And for V, you can use a line coming out like this. You can think of these as kind of bonds, or sort of unpaired electrons or something, if you're thinking in chemistry language. They're kind of dangling bonds that want to mate with or connect up with some other bond. And if all the dangling bonds are gone, then you have a scalar. And depending on how many remain, you have a tensor of that particular type. So what I didn't yet say is that there are two types of abstract indices, which have the same names that you're used to. Contravariant indices, or upstairs indices, which correspond to the vector space V, which, as I said, will almost always be for us the tangent space of the manifold. And then the covariant, the names are actually somehow backward from what most people would find natural, but for some historical reason. Because this means varying in the same way, and this means, oppositely varying. So the things that, like V, which is what we started with, are called contravariant, and the things that correspond to V star, which is the dual, are actually called covariant for some reason. So every index, and these are, of course, contravariant means indices like this, and covariant, they're represented as superscripts. Covariant indices are represented as subscripts. So now we have, and so now using this index notation, we show contraction. How? Just the way you probably would have, you already know the answer. Probably, we represent contraction by repeated indices. That is, we use the same letter twice. That shows contraction. And we represent symmetry operations by permuting the indices. And we can only permute indices of the same type, meaning contravariant, all contravariant, or all covariant. So let's look at an example. Or also, if we use these other kind of pictures, now you see why I put these coming down and these coming up, because that's supposed to be a contravariant. That's supposed to be contravariant, corresponds to a contravariant index as to covariant. If we use those, then we represent contraction. I won't write it out, but contraction we represent just by linking together two bonds. And permutation we represent symmetry operations we would represent by braiding, if you like, the two bonds, right? Something like that. That would be a symmetry operation. So let's look at a particular example of contraction. So given this metric tensor, here, GAB, and a vector in V, not a covector in V star, we can, of course, well, now we can't contract between here and here because they're the same type of index. Did I say that? We have to say, I should have said that's important. One co and one contra variant. So you can repeat a letter, but one has to be upstairs and one has to be downstairs. So we couldn't contract A with, we couldn't write GAA and show a contraction. That's actually why we're free to write GAA sometimes, which I like to do. I've already done it once or twice. But it doesn't mean a contraction. Where it does mean a contraction is one is upstairs and one is downstairs. So in this case, we could write GAB BB. That's a well-defined contraction of the tensor. Well, it's a contraction between these two indices. You could also regard it as a contraction of the tensor GABVC on on these two indices. And that's what I've shown here pictorially. This week sometimes, or we will almost always, when this is the metric tensor now, we'll always use this notation where we call this V sub A. So it's called raising and lowering indices. We can also go further. Well, that was a good example of relative motion. I thought this was coming down, and I tried. Almost got dizzy because it was. I pushed. So this gave us a covector from a vector. We could go further and put in another vector of VA and VB. That we would call V. We could notate that as VA VA using the same notational rules. And of course, that's a scalar. It's just the length of the vector V according to the metric G, or the length squared, I should say, of the metric. So that's how you notate contraction. Remember, if you want to know what that really means, you have to go back and write out GAB as a sum of products of covectors, and V as a vector, and then contract that vector with the corresponding covector in each term in the sum. And so now let's give an example of symmetry. So this shows how to represent contraction. Oh, I have more space. Let's go. Now, how to represent symmetry operations. So let's take the tensor T that we had before is equal to U tensor V, and then T tilde is V tensor U. Okay, so here I'm using the explicit tensor product notation. This is the kind of notation like quantum information people like, for example. And it's also the kind that mathematicians tend to like. How would we notate this in the index notation? First, I want the definition of T. So this said that T was the tensor product of two vectors, so it better have two indices like this. And how do I say that it's the tensor product? Well, the two vectors, they have indices to show that they're vectors. Not U, but V. And so this is how we represent tensor product. So notice that I have not used this sign. I don't need it anymore because the indices show it. In fact, I could just as well write it. This is important. I could just as well write it this way. These are not different tensors now because I kept the same indices. I mean, the index A moved along with U. Okay. So I could write it either of these ways. However, what about the tensor T tilde AB? what was it? It was V. It just comes from reversing the roles of U and V in the product. So that's V A U B, which I could also write using what I just said before, is UB VA. And having written it like this, I can pair with the definition of T. That was just UAVB. This is UBVA. It's the same definition, except obviously B and U and V are the same here, but B and A have gotten exchanged. So I call that T, using this definition here, it's correct to call this TBA. So the way that the symmetry operation gets notated is that T tilde, the swapped tensor, or what's the exchange product, is just equal to B with the indices reversed. Right? So A and B have no absolute meaning. I could have used any indices, any letters here whatsoever. But what's important is the relative positions of the indices in these two tensors. This is the tricky thing. So this shows us that T tilde is T with its indices, with its factors reversed, right? And of course that means reversed in every term. When we write out T as a sum of products, we reverse in every term. So let's take now an example. Well, first of all, if T is symmetric, it's called symmetric. If and only if, of course, T is equal to T tilde. And that means, as we just saw, that TAB equals T tilde AB. That's a trivial step. And that's equivalent to TAB is equal to TAB. So that's what we mean by calling the tensor symmetric. So now taking an example, GAB we know is symmetric. Well, GBA. Let's say we don't know it. We do sort of know it. Yeah, we know it. I think I forget when we discussed. Anyway, this is true. It's symmetric. I think we actually gave enough information to prove it. But if it's symmetric, then it means that it should be able to be written in such a form as a sum of products that you see when you swap the products, that you get back the same one. So that means you write them out, then you swap them, then you use this rule for wherever it is, when two tensors are equal, and you see that GAB equals GBA. But there's obviously a special case in which it's trivially apparent that it is symmetric. And now I'm going to, for this equation, I'm going to not write the indices, just to not confuse things. So, because it just to create more the kind of confusion that came up before. If G was just a product, so this does not use the abstract index notation here. It's going back to the other notation. If G was just a product of some vector with itself, of course it would be symmetric. That would be trivial. Because if you have a tensor U tensor, if you have a vector tensor that's U tensor U, or U is a vector, obviously if I exchange the roles, the two factors, I get back the same tensor. So G should be, you might expect, it's not trivially obvious, but it's not obvious, I guess I could say, without a little more work. It doesn't follow that just because G is symmetric, you can always write it in this form, unless you prove that theorem first. But in fact, you can. So I'm taking 4 vectors, which I've called T hat, X hat, Y hat, and Z hat. The notation is obviously suggestive. So T hat x hat, y hat, and z hat. Those are elements of V star, right? Because these are actually, G is meant to be a covariant. So take these 4 covectors, and we can write G in this form. Where, in fact, further, as you probably know, well, no, what am I trying to say? Once we've written it in this form, then it turns out that these things will actually be, these t hat, x hat, y hat, and z hat will form a basis, and in fact, they'll form an orthonormal basis, where orthonormality is defined with respect to this metric tensor itself. But that's not the main point. The main point is that G can be written in this form, and then its symmetry becomes manifest. And conversely, the fact that it is symmetric should strongly suggest to you that you might be able to write it in this form. The more general, anyway, so that answers, someone asked, did you? Someone asked this question.
Anton.
You asked it, okay. In general, so that's an application to symmetry of the metric tensor. And in general, any tensor, this came up before in some other lecture. Now we can write these formula. I probably wrote exactly the same formula, but these are now abstract indices. That's the only difference. Any tensor can be, by adding and subtracting its t tilde, the corresponding t tilde, any rank 2 tensor with both contravariant or both covariant indices, so that symmetry makes sense, it can be split up uniquely into 2 pieces, one of which is symmetric and one of which is skew symmetric or anti-symmetric. And this belongs, and so that what that tells you, again, just to reiterate, is that this piece, when you write it out as a sum of products, if you swap all the factors, you get the same thing back. And this piece, when you swap all the factors in each product, you get the same thing back with a minus sign. And these correspond to these Young tableaux, which are only the tip of the iceberg of these Young tableaux. So every tensor belongs to some symmetry type or some sum of symmetry types. It may not be symmetric, but if it belongs to a pure symmetry type, then it's either this or this, if you have 2 tensors. But if you have 2 indices, but if you have 3 indices, there are more symmetry types, and if you have more, like 4, then there's quite a few more symmetry types. That just to say something interesting, the Riemann tensor also belongs to a symmetry type when you take all of its indices as, say, covariant. And it actually turns out to be this symmetry type. That's a concise way of saying all these rules that you may have seen before about cyclic permutation and blah, 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 for the Riemann tensor. So the last, okay. So are there any questions on any of that? Contraction?
So
yeah.
If something isn't a tensor, is it not possible to write it as these tensor products? Or is it still?
If it's not a tensor, then it shouldn't be written that way, yeah. I mean, if you write it that way, you're saying it is a tensor. But on the other hand, you might have in mind, if you had in mind something like the Christoffel symbols, then they're not a tensor, but you can still write them with, we haven't yet introduced the concrete indices, which we'll, I guess, do next time when we talk about components. But when you write something like this, it's definitely an array. It has indices. So you might write, could I express, this is now to be interpreted as a set of 64 numbers, which you could think of as living in a cube, right? I mean, if you have just 2 indices, you can think of it as a matrix, and if you have 3, you could think of it as being in a cube. You could ask, could I express those 64 numbers as sums of products of just row vector? I mean, just, you might ask, could I find things like A, B, and C, A alpha, B beta, and C gamma with some index here that just, you know, so this, I could have called them A, B, C, D, E, F, and so on. But will there exist A, B, and C? These are now just strings of numbers, what a computer program calls a vector. Could I find A, B, and C to make this true? Well, yes, I could find A, B, and C to make this true. Because I don't know, these are just numbers. They might have been the components of a tensor. Why not? If they were, then I should be able to do this. But it wouldn't be correct. What it would not be correct would be to convert these into abstract indices, or to write them in that other form. You know, so this gamma does not belong. When you ask what kind of object physically is gamma, it does not belong to V tensor V star tensor V. Right, that's, from looking at it, that's what you might think it belonged to, but it's not actually an element of that space. It's very tricky because if you pick a coordinate system, you can find an element of that space that has the same exact components that gamma has. But if you now pick another basis, you'll find that that same element doesn't have the coordinates of gamma in the other basis.
So you say that the tensor has a coordinate invariant representation like that, but something that doesn't have.
If you yes, you could definitely say that. The tensor has a coordinate invariant representation of this form. And yeah, that would be exactly right. And something that's not a tensor cannot be written in this way. But the word coordinate invariant carries a subtle implication that you're really thinking of the tensor as a bunch of components, which is what I'm trying not to do. But if you want to, another way of saying it, and we'll see this later, not so long from now, maybe in a homework problem, is if you write out the components in a given coordinate basis, and then you switch to another coordinate basis, a different coordinate chart, and you ask how do the components transform when you go from one chart to another, you'll see that these transform in some multilinear way. Tensors transform, whereas this transforms in an inhomogeneous way. It doesn't transform, and its components do not transform in the same way that the components of a tensor would transform. That's the more old-fashioned definition of what a tensor is. It's just a bunch of numbers that transform in such and such a way under a change of basis. And it's still one that you'll see a lot, I think. The last thing I wanted to say was tensors as linear mappings, but maybe, well, okay, I won't quite get finished. Let me just think, I'll come back and start here again, but let me give an example, or just let me state the basic idea. By using contraction, we take a fixed tensor T, say, just make one up like this, and then we contract. We take some other kind of tensors like S, B, C, and by the process of contraction, contracting this with this, we would get T, A, B, C, S, B, C. This belonged to the space V, tensor V star, tensor V star. This belonged to the space V, tensor V. This belongs to what space? These two indices are gone now. I meant to say that was an important thing. These indices that are contracted are called dummy indices. And one of the rules of the notation is that you can replace a dummy index by any other letter as long as it doesn't clash with the letter that you're using somewhere else, and it has exactly the same meaning. So like, that I should have said before. So let me just say it again. So for example, just to say VAWA is defined to be exactly equal to VBWB. So that's the rule for dummy indices. These are called dummy indices, and they're gone, right? So whereas this is called what's left over after the contraction, or maybe it was just there in the beginning before you started the contraction. in the context of this tensor, A, B, and C are called free indices. B and C are free indices here, but after the contraction, only A is a free index. So of course this belongs to the vector space V. This is just a vector now after we contract. So what have we done? So let's imagine holding this fixed and letting this vary. Then for each S, we get, which is an element of this space, we get a contraction, which is an element of this space, namely a vector. So we've produced, holding T fixed, we've produced a map from D tensor V to V. And that's a general thing. Any tensor can be used in that way to produce many linear maps between other tensor spaces. And conversely, any linear map between tensor spaces, in other words, any linear map from one space of tensors to another comes from, in some sense it is, itself a tensor. So this is one of the most, so we've seen actually a lot of examples of this. Like when we defined a covector as a linear map from vectors to scalars, we got a tensor, in that case a very special kind of tensor. We also at some point defined the metric tensor as a linear map from, well, we could have defined as a linear map from V tensor V to scalars. Anyway, I'll say a little more about that, but that's a very crucial fact, and that's the sort of second way of thinking about a tensor, is a linear map from one space of tensors to another. Okay, so I think it's getting a bit late. So before we break, are there any questions on this and what we've done? You had a question?
I was going to ask if is there a notion of exponentiation of vectors?
No. Well, not without something else. Well, you were thinking of something like, there is something close, maybe I should say yes, I'm not sure. Especially when you're talking about Fock spaces in quantum field theory, there's something that you could write as a notion of exponentiation. It depends. If you're willing to generalize the idea of tensor, which you can do beyond what I've just, I've just defined tensor spaces like V, V tensor V, V star, and so on. But you could imagine, maybe I can make up some sort of more general space which allows me to add tensors of different ranks together. If I could do that, then I could invent a notion of exponentiation of vectors. So I could say e to the v. Let's say u is easier to write. So e to the u, I could say 1, what do I want? 1 plus u tensor u plus u tensor u. And now I can put over 1 factorial over 2 factorial. So now, see, this doesn't live in any tensor space that we've ever considered or will ever again consider, I think. But in quantum field theory, it's natural to consider this is how you produce Fock spaces, basically. So this is some more general space, which is basically mixing, mixing different particle numbers in the context, which you do all the time, of course. You consider spaces which are Hilbert space vectors, which are superpositions of different particle number. And so it's natural in that context, and then we could call this the exponential. So in that sense, you might say that there is a notion.
So then you could talk about,
And then you want to consider the fermionic analog of this.
I was thinking like the tensor product 1/2 times.
That I have, wait, to the 1/2 power, I have absolutely no idea what that could mean.
Well, I mean,
But
you could define the log the same way and then just go to the 1/2 log.
yeah, it's true. Log, Yeah, the power series doesn't converge very well for log, but yeah, if you could define a log, that's the problem. The power series for log isn't very useful in a lot of cases. I mean, it just doesn't work as a power series. It has a finite radius of convergence and so on. Only for small things near enough to 1 can you write log as a power series. I mean, I wouldn't be surprised if someone has done it, but I can't think right now what would be a sensible definition. But anyway, so this space you might call this E to the V, now being the space, right, of all of these things. And it's natural, as I said, to think of the Fock space as E to the V, where V is the one particle Hilbert space. So other question? Okay.